Hello and welcome to this, our fourth webinar for 2014. I would like today to talk about drill hole management and mesh grid operations in GeoModeller. This is our fourth webinar for 2014 and it is actually a pre-recorded webinar, which is unusual in our series, but it was necessary this time due to the Easter holiday break affecting many of our regular listeners and staff here alike. So apologies, we'll resume as normal with live webinars commencing next month in May. I'd like to straight away begin with our format of today, which is to go through a PowerPoint presentation and then to proceed into a demonstration with GeoModeller software. To begin with, we'll have a rhetorical question. Can one build a GeoModeller model from drill holes alone? Yes, the answer is, and that's very useful because not always do we have surface geology available, and neither do we have complete outcrop or any outcrop in some cases. So it is useful to know that we can build a model on drill hole data alone. And just as a revision, what are the steps to set up a GeoModeller model? This is partly revision from the January webinar, so I can just go through those again. When you set up a model in the first instance, we need to set the project extents by way of their datum and projection system and the extents in northings and eastings within that zone. The second step is to load a digital elevation model, and the following are input formats which can be supported by GeoModeller. For example, DXF points, contours or 3D faces, a regular grid such as a .ers, .grd, an arc grid or an ASCII grid. Also geotiffs are supported by GeoModeller, and when these are loaded as the digital elevation model, they'll be reprojected and trimmed to the project on the fly. Finally, irregular grid formats are also supported, and the most convenient of these is a semi-format, an ASCII style, and these will be regridded at the time of uploading, and the user will have the choice to select the resolution. So step number 3 is that we will import the drill holes as a 3-file system of CSV, and they will be collars, surveys and lithologies. And if the logs are well structured, it's possible to create formations on import, or if they're not, you can also choose to select to set up the geological objects prior to importing the drill hole data. And a second step, separate to loading the drill holes, is to add numerical data to the downholes logs. And this could be any type of numerical data, including, say, assays or densities. They can also be the geophysical logs in a second step. The fourth step, let's create a geological pile now from our geology objects. And we're going to remember to be able to group together geological units which have concordant relationships, and we're going to group them into series, and then finally we're going to set the intervening relationships of the pile, which could be onlap or erode. In the fifth step, there's a chance now to add orientation data for every geological series in the geological pile. It's necessary to do this so that you will be able to compute the model. In the case of drill holes, it may not be necessary to add new contact data because a drill hole intercept in itself counts as a contact data point. And if there is one existing per formation of the geological pile, then a compute of the model is possible. Just to think a bit more about step number 3 in detail, about loading drill holes to the project. There's a mechanism by way of a 9-page wizard which creates and sorts the formations on import. And here's some examples. With the grey units, BG2 and BG1, the model hasn't seen those before, so it's suggesting to us that we may want to create the formation on import. If, on the other hand, units have been set up as geological objects before, not even necessarily put to the stratigraphic pile, but just in existence, then GeoModeller will recognise that whilst importing drill hole data, and it will suggest to import and merge to an existing formation. A third option here in the last point, down at the bottom, is that we have two names which are seen by GeoModeller on the way in. This drill hole has a unit called HJ and also has a drill unit called HHJ. They are known to us as the same unit, but by a different naming nomenclature. And so our choice may be to merge the two formations, and so the first one is imported and the second one is merged. Just to summarise those number of options at step 3, we are able to create a formation on import. We are able to import and assign an existing formation. We are able to import and merge to an existing formation, which means all those three types are covered, and it's quite a flexible system when we're doing a drill hole import. Another choice is to simply not import and create any type of geology unit for some of the lithologies in the drill hole. And once that is done, the drill holes are loaded. You can visualize them straight away in the 3D. And another thing is that the project will need some type of orientation data for each of the units or each of the series in the geological pile. And here they are shown as little cones where the azimuth and the dip is illustrated in 3D. Now to discuss something about the tools and techniques for analysis and visualization of downhole numerical data, for example, assay data. When we import, the wizard will look something like this. From the main menu, we can choose Import, Drill Hole, Assay Data to Existing Drill Holes. And this is a type of format which we can analyze a little bit later, but there are standard CSVs with space or tab separations in an ASCII file. Visualizing the drill hole data after import is a straightforward possibility, and we can see here an example of assays stored in the from and to zones of the drill hole structure, together with the logged geology on the left and predicted geology on the right. Here are the two columns, geology on the left and model geology on the right, together with all the numerical downhole data now loaded to the drill holes. Another thing we may want to do next is to prepare the drill hole log data for interpolation or kriging. So assay sample intervals may be of variable length and must be composited into equal intervals before most interpolation techniques can be used. Here we're going to prepare data from the interpolation main menu, and we're going to suggest to change drill hole fields to regular intervals. The wizard will lead us through this step, but the idea is to select each drill hole from the list, and you may leave drill holes out if you want to do a selective choice. On the right hand side, you have to select a field in which you want to have regularized sampling. Next is to create a new grid name and choose the support size. So for instance, 10 meters is selected here, and that would mean the support size will produce a new weighted mean value for the new mid-interval point every 10 meters. When we view the log again, we have a new field come up on the right hand side. This is our regularized constant interval iron for 10 meters. Next, we may want to transform the drill hole assays to a vertex mesh. This is by way of creating a new mesh which can be whereby the center points of each regularized assay interval is stored as the vertex, together with the numeric data for that interval. And when we do this, we access the main menu, Interpolation, Prepare Data, Drill Hole Fields to Data Point Mesh. Note also that most of the main menu items are available in context-sensitive menus in the Explore tree, and so it's up to you the choice of accessing it through the main menu or the Explore tree. When we do access, for example, through the Explore tree, the choice is to select the field in which you're interested in by expanding the plus to a negative sign and showing all the available fields in the one mesh. And then it's a selection and then a right click. This will open up the menu, for example, on the right-hand side, and a lot of processes then become available to us. For example, we can visualize the metadata of the vertex mesh either from, as we said, the Explore menu or the main menu. And this will allow us, for example, to see under exploratory statistics the histogram. The metadata of the mesh is available to us here. So for example, the number of effective cells, the total number of cells, the number of nulls, and the percentage of those which are nulls, minimum, maximum values, mean and standard deviation, etc. So this example is showing us the histogram of iron for the 3D grid. This now includes, as a mesh, all of the drill holes in the data set, not just one drill hole at a time. Another choice we may have is to prepare a crossplot of several fields of the one vertex mesh, again by either the Explore or the main menu. So under the exploratory statistics, it's possible to do a multi-crossplot, and here you can see the field of the wizard is showing us that we can tick several against each other to analyse and choose to do a regression analysis at the same time. This is a multi-crossplot. The top one is showing us the histogram of iron content. The lower right is showing us histogram of SiO2 content. And the one here, the linear regression, shows the crossplot of iron against SiO2. And it shows it on the basis of, in this case, all the geological units within the model and the volume represented by colour. Another choice is that we may want to add the lithology index of the current model field to any of the mesh grids that we are working with, either a 3D vertex or a regular grid. And this is useful because we then may want to mask the numeric data using a lithology type. This is how we would create lithology field indexes allocated from the stratigraphic pile. What's happening here is GeoModeller is automatically choosing that the above topo or airspace has an index of 1, then it will return to the base of the pile and upwards assign a lithology index from 1 to the maximum number of units in the pile. You need to take care though that sometimes it's possible the indexing will change, but only if you choose to compute your geology model in 3D by only selecting some and not all of the units in the geological pile, and this could impact on the indexes changing when the current model field is copied to the grids and meshes area. One thing to just be mindful of is that we're going to concentrate on the OR2 geological volume. This has an index of number 4. This allows us to do another step in our workflow, which is to create a new field masked by a limited lithology and its volume. So using the 3D calculator, we can obtain iron values that are contained only within litho unit 4, which is OR2 horizon in our 3D geology model, so that set iron values in all other units will become null in a new field. And so you can just see this is showing the wizard, and on the left-hand side we have a list of all the fields available to us within this mesh, noting that we've also added the current model grid. Once we set up the argument, we can allow the new field to be computed, and we have to also give it a name. So in this case we have a statement which says if the current model grid is equal to 4, then provide iron, otherwise place a null in the new field. The choice then is to evaluate and then save and exit from the 3D calculator. Next, we are able to visualize the result of our new iron vertex mesh in 2D and in 3D by doing a projection to a section, in this case in the upper view, and down below we have the 3D model of the same. Also, we are able to do some controlling of the visualization of the mesh using the lookup table editor. And some of the features here are that we can manually adjust the transform. We can also allow manual or automatic clipping of the data limits. We can allow manual or automatic setting of the visibility clip for data limits. Also, GeoModeller allows you to add extra lookup tables which you may want to import yourself as the user. So to have an example of other ways we can mask the 3D mesh, here is a choice just using the lookup table by which we are able to hide values below 50% iron. Next, here's an example of we can use 3D masking to hide values above iron equal to 50%. And again, using the lookup table, a choice whereby we can apply a stepped lookup table transform. This enables us to bin certain colours for certain grades of iron. And finally, just to show you what is available in all of the interpolation methods listed in GeoModeller, we are going to demonstrate today with the inverse distance interpolation or the inverse distance weighting method, but others are available, such as kriging in 1D and 2D, domain kriging, which is very particular to GeoModeller and probably is worthy of its own webinar. And there are two methods involved in the choice to set up domain kriging, which is essentially using the field lines of our potential field method of building an implicit surface. So quite cleverly, this type of kriging allows you to make an interpolation not as a straight line, but along the field lines of the geology body. This means, quite usefully, you don't need to unfold a very complex geological unit in order to krig and then fold it back again. So domain kriging provides an answer to that situation. Gaussian simulation on a domain is another type of interpolation method available in GeoModeller. So now I would like to end the PowerPoint here at this stage and provide for you a demonstration in GeoModeller for drill hole management and mesh grid operations, including an example of inverse distance interpolation. Now I'd like to start today's demonstration. So here's the open application of GeoModeller, and we're going to move to the main menu and ask for project, looking for a previous list of files that have been open, and we're going to select Iron Proj 1. This is a synthetic iron ore model. The extents of the wireframe are something in the order of 2 kilometres by 3.5 kilometres, and we have already pre-built a 3D model here on the viewer on the right hand side. You can see how it looks in this case. Also, I'd like to show you the stratigraphic pile. Notice that this project's been built with a reference of tops, and it's a simple model broken into separate series of 5 different geological formations. We'd like to view the DTM. This shows us all the sections which exist in our project. And now to proceed, I would like to first of all hide the geology model to see which drill holes are existing already in this model. This is a model that is only constrained by drill hole data plus some orientation data also. So to view our drill holes, we're going to go View 3D Viewer and show the drill holes, selecting all of them and putting them on an exaggeration of 25 meters in diameter. At first they only show by a fine trace, and then we will need to use the Explore tree. On the left-hand side, we're going to select drill holes, right-click, and choose to rather show them, and to show them with a shaded pattern. That brings up the exaggerated radius that we just asked them to plot at. So here we have them. All of our drill holes are around about 148, and no surface data, but there are orientation data just to link together some of the contacts and be able to build a 3D model which is making sense. Let's have a look now at some of the data. You can see, let's say, one drill hole at a time. We're able to select in the active 3D viewer. With a right click, we're able to edit a drill hole. So this is drill hole S34. It immediately can pop up and we can see the log of geology on the left-hand side with the model geology on the right-hand side. What also is available to us is the ability to do some editing here. So for example, if we had some collar location problems and we needed to change these, perhaps because there was a slight mislevel in the relative level of the collar compared to the DTM or vice versa, these numbers are all interchangeable and editable right here. And also, if there was a misassignment of a geological formation, it's possible here to choose another one and reassign geological intervals in this interface. Likewise, any of the from and to values can be changed here. If you do make a change here, it's fine to back out of that easily just by closing the window. When you reopen it again, things will be exactly as they were. But had you wished to preserve the changes, then you would have needed to go to Drill Holes, Save, and that would allow you to ensure that the changes to the drill holes are going to be preserved and to remain that way hereafter within the project. These drill hole changes don't push back to any database outside of GeoModeller project that's current, but they will stay within this project of GeoModeller, the changes to any drill holes that are made. So if you would also like to interactively work with drill holes, we can release the view of the 3D viewer by double-clicking in the black background, and that will bring up our 3D view again. But if you also wanted to see the drill holes and touch them for editing purposes, you can expand all of the drill holes available in the Explore tree, and that is, of course, we can scroll down to the same drill hole, was S34. Double-clicking allows us to see the same drill hole here, and likewise if we were to project onto the DTM, we can see them in the 2D viewers as well, and that's by model, project, yes, project data, and choosing the drill hole trace and the drill hole contacts, selecting all of the geology data involved, and saying OK allows us to project the drill hole data onto the 2D section. These will show up with little caps, which makes it easy for us to see where they're located, particularly in relation to any of the sections. If I was to select the drill hole again, I can right-click, not on the section line, but on the drill hole itself. If I was to select the drill hole, I can do it from here, S34, and edit, again to show the trace of drill hole S34. Next, I would like to show how we can compare the drill holes with one another. So first of all, let's highlight section C7, which clearly the drill hole lies upon. We'll double-click that section C7, and now we can see a view where we can project all of the drill holes from that section. And just to show you from here, section C7 in the 3D viewer is also available. But here we'd like to now project them onto the 2D view. So that is from the main menu, Model, Project Data to Sections in the 2D viewer. Section C7 is the target section. We'd like to see all the geological data onto this section from the drill holes, both traces and contacts. When that comes up, you can see that there was a projection distance, and so from either side of that we're able to ensure that we're bringing onto the section everything from the projection distance. And I'll just repeat that to show you what that was. It was 20 metres. So 20 metres from either side, we're going to pull the drill hole data onto section C7, and that's what we've done here now. And again, just for completeness, here if we highlight a trace of our current drill hole, this one's S35, but this one here is S34, which is what we've been tracking. Again, you can edit directly off the section. One thing I'd also like to do is to, at this view, show the model against the drill hole data. Knowing what we do about the compute step, which is already done, we can then choose to plot the model onto section C7. So section C7 is highlighted, and next we'd like to show the lines for just a normal resolution. Going ahead to do that, we now see the plotted lines. Remembering, if you wanted to view our model in a more solid fill, that could have been done as well at this point. And this is how the model would look. You can also take that model slice across into 3D by Show Modelled Polygons in the 3D viewer. And here it is across here in 3D at the same time. Now, the purpose of showing this section was to have a look at the model data compared with the drill hole traces. We already have an opinion on what they would look like because we've seen the two traces side by side in the log now several times from several different views. Now, if I can just restore it to the line model, let's go to Display Parameters and hide the fill for the time being. What I'd like to know is to see that how much misfit there is between the drill hole constraints and the model itself. So you see we will be expecting some. You would see that the top of the red here in this drill hole intercept is a fair distance away from the model, even allowing for the fact that this drill hole may have been projected by up to 20 metres onto section C7. Let's do a check now on one of the menu items, which is called Model, Compare Model with Drill Hole Observations. Again, we're going to choose a precision, and I may choose, let's say, 2 meters precision. So I'd like to now question, for every drill hole in this entire project, how many drill holes do not fit well for a precision of 2 meters with the model. The answer takes just a little while to generate, and you'll see on the left-hand side we're going to expect that some of the drill holes in the Explore tree will go to a different colour. Also, we'll expect to see that some of the caps on top of the drill holes will become filled, and these will be our problem drill holes. And then we have our first drill hole, which is shown to be in disabeyance with the model for a precision of 2 meters. There is at least one contact here not agreeing. And if I close this dialog for the moment, just so I can see all of the drill holes here in our Explore tree, you can see here the red colour. This is the equivalent of saying there's a cap on top of that drill hole because there is a problem with its relationship to the model. And here's another one. And that is all. So there's just 2 drill holes here which don't agree with the current model. And one of them is this one, S75. There could be a couple of ways to remedy this situation, and the one I'd like to highlight is to say that with such a large richness of drill hole data, that it is possible to allow too much model smoothness, and therefore it needs to sacrifice fitting some of the drill hole intercepts for having some amount of smoothness. This is something of a high-level topic which is available to see in the manual, but for now I would like to just show a solution which allows us to replot or recompute the model, taking account for the fact that we would like to sacrifice some smoothness. We want to make the model a little bit rougher, and we want to do that to achieve a better fit to some of our drill hole intercepts which are not currently fitting well. So let's just have another look at that for the sake of giving a quantity on how bad the fit is. You can see here for our drill hole S75, the misfit is at 17.28%. That's the amount by which this contact in the log disagrees with the model in its current build. Returning again to compute the model, this time I would like to say that OR1, which is the red unit, the top of OR1, and I'll just show you the stratigraphic pile to let you know what I'm speaking of here. We're referencing tops in this model, so the top of red is the top of OR1. This is the contact of concern. Therefore, we choose OR1 in the series to interpolate. But before we go on to do that computation, I'm going to choose the parameters of OR1, and I'm going to modify them. You can see in the detail here there's something called nugget effect, and currently it's set with 0.50 and a 1. In order to force less smoothness but greater model fit, I'm going to add a couple of zeros in here. This is the way that this function works here. But don't forget also to go back to a select all situation. All we've done is set the parameter of the nugget effect inside of OR1, but we also need to return to the state of interpolating using all of the series, all of the sections, and all of the drill hole data. So let's proceed to do this compute. When the compute is done, we can also proceed again to show the lines of the model against section C7. And you'll see there is a closer resemblance to the fit. Just again reminding you that these drill holes are projected onto the section, so an exact fit may not be necessary or in fact required in the three-dimensional view. but what we would like to see is a greater more improved misfit, and let's do that by editing the drill hole and seeing that the misfit has dropped from 17% down to 4.9%, and indeed this model is now obeying the drill hole intercept to a much greater degree as expected by altering the nugget effect. If we were to repeat model, compare model with drill hole observation for a precision this time of 1 meters, and to compare the drill holes again throughout the entire project, and it takes some time, we would expect that the cap shall be disappearing from this drill hole in question. Indeed, the drill hole now is compliant with the precision of 1 meter. Now, with that part of the demonstration complete, I would like to now head into loading the drill holes with numerical data. And that is something that now can be done using the main menu area. And what we're going to do is say import drill hole numeric data to existing drill holes. The wizard will take us through just 3 steps. We're going to be able to browse to a file which is already in our folder, an set of iron project data. The next step is to parse the file, and if I can separate that out for you, you can see the format. The columns have been recognized, and but otherwise it could be a chance to use the text qualifiers or to start at a separate row compared to the first row if you do need to parse the file correctly. One thing to note here is that the nulls are set at -9999, and that is something you just need to remember and be aware of, because we're going to instruct GeoModeller of that fact. And all we need to do now is go on to the next wizard page. Now, selecting one column at a time, we just need to tell GeoModeller what to treat each one as. So this is mapping the columns. The first one is hole ID. The second one is a from. The next one is a to. Geology we don't need to touch the column of. Iron we do need to treat as a field. A description and a unit is not necessary. These could be just a text addition. But what is necessary to add is what is the null value given in the case of iron. So that's -9999. And move on through each of these in turn. For AL203, treat it as a field and provide the null value. Likewise, magnesium as a field. And finally, SiO2, treating it as a field and providing the null value. If you wish for iron, you can describe it as a percentage. And when all is assigned and mapped, we can just finish. The work is being done now to import all the numerical drill hole data and load it to each file to each drill hole in turn. And we have a report here which says that they've all loaded 158 drill holes in this particular data set. So that is fine, and now we may see the effect of what we've done, which is to open any one of these and have a look at the edit now. Again, we have our 2 columns shown on the left-hand side, the geology and the model, But now we have 5 fields. Each of these are the numerical values as just imported: iron, Al2O3, manganese, and so forth. You can see the fields one by one. And so, for example, if I was to now click on iron and right-click, I could see the iron just in one drill hole. This is a histogram and also showing the metadata only for the drill hole data in one drill hole at a time. Likewise, we can still do something like a crossplot if you touch the upper level of the fields. And we could do a crossplot analysis here, let's say iron against SiO2 with a regression. But again, we're only treating one drill hole at a time, so the results are not going to be particularly of interest, although this, of course, may be some necessary part of a workflow to inspect each drill hole at a time. But we're only looking at a small amount of data here. So I'll just close that now and move on to the next stage. What we'd like to be able to do now is prepare for interpolation, and we'd like to be using all of the drill holes at the same time. So working off the explore tree, I'd just like to take the upper level where we're talking about drill holes, select it, and then right-click on the menu that says Fields to Regular Intervals. This is now asking us to select all drill holes, if that is what we choose, and we see now the available fields, the 5 fields. This time we're just going to select iron and Al2O3 with a support size of 10 meters. This is the regularization process. We're going to select 10 meters over is the new sampling interval. When that's done, it's a simple step, but it has produced a result for us, and it's able to be visualized by editing the drill hole and seeing that we have another field in here. So the field that's been added are 2 fields: the regularized iron at support size 10 meters and the regularized Al2O3 at support size 10 meters. So you can see that effect. Also, another field is of course added into the editable part of this drill hole log. The next part of the step, rather than have everything in a separate compartment, we want to change all the fields into a data point mesh. That way they can be manipulated as a whole. So in the Explore tree, we're going to right-click again on drill holes, and this time say Fields to Data Points Mesh. Again, we get some options, and we're going to select all the drill holes to include in this new point mesh. We're going to now select just the regularized iron, which means turning all the other fields off. Actually, we'll take both of them together. That way we can do some cross plots on the whole later as well. Just select OK and the work is done. Interestingly, this time now, for the first time, we have a new grid or mesh presented here under the Explore tree. Previously we only had the 2D elevation grid, but now we have a little 3 here against this grid, and this is our first drill holes fields mesh. It's a point mesh containing 2 fields, regularized iron and regularized Al2O3. Just to show you now that we have an ability to now view everything as a whole, we can right-click on regularized iron and this time go to a histogram, which is much more populated with data, because it's showing the entire mesh at the same time. So here's the histogram of regularized iron, showing a nice healthy peak above 60% iron, and also the metadata here is shown, so the number of effective cells is visible compared to the number of total cells in this particular mesh, and other various facts on minimum and maximum ion grades and so forth. Likewise, we can do a cross-plot analysis by choosing the two fields that we have regularized, and let's do a regression on that. The field shown now. Here is our linear regression. It's showing the cross-plot of regularized iron against regularized Al2O3, and for comparison, the two histograms, upper left is the iron and lower right is the Al2O3. And that is an interesting relationship from the point mesh, all of the drill hole data. So it's important to note at this point that iron is log normal, as was just demonstrated in our views, but interpolation is best performed on a normalized distribution. And so what I'd like to do next is to use our 3D mesh calculator for the first time, and therefore we're going to select the new mesh, drills, holes, fields, and we're going to compute a new field, and this brings up the mesh calculator with the two fields available for us for doing computations upon. The argument I'd like to set up is to say that the natural log of iron, regularized iron, is what I am seeking to create in the new field, and give it a name called log of iron. All that needs to be done now is to evaluate and save and exit. So you can already see that the third field of the new field has been created, the log of iron. What next happens is that we can save and exit, and the new field is also shown under the grids and meshes. If we do a right click on this field, we could now do an inverse distance interpolation. But before I do that, I would like to show you the result of what we've done to date. Let's just hide the drill holes now. We'd like to have a look at our first mesh. Using the field of regularized iron, let's go to Field Visualization Manager and view it in 3D. So here, as I was mentioning before, we have a point mesh, which means that the entire data set is connected and understandable in one sense, so that when we did a histogram analysis, all the statistics were from the point mesh as a collective. That's very important. The other thing that's important to show is that we can edit the clips and colours of this, and we can show that any type of colour stretch we like, we can modify this as a custom curve. We can also choose to show a limited data clip or a limited visibility clip. If we choose to show a colour stretch whereby, let's say here, all the values greater than 60% iron will be in red or white, let's apply that change. And there we have it. We can view that by double-clicking on the 3D viewer. You can also expand to have a much closer look at the numerical values in our point mesh, now with the new lookup table. And if you wanted to see the colour table, it's also possible there through the Explore tree. So that's the point mesh. Now we're actually going to perform the inverse distance interpolation using our point mesh. So now we want to select over in the Explore tree the log of iron in its point mesh. And if we do a right click on that, we can choose our method, which is going to be inverse distance interpolation. This takes us to a 3-page wizard, and first thing to do is to define the target grid. We're going to call this one log of iron and move on to the next step, which is setting up the grid definition for kriging. This is the resolution of our target grid. I'd like to type in a choice here of a fixed cell size, 25 meters. The next thing to do, and in order to set this value you would have perhaps been advised to have done a variogram analysis to have a better feeling for what could be the maximum radius of the neighbourhood that is a good search distance. But in this case we're just going to show you through the stages of this wizard rather than try and do an elaborate geostatistical demonstration. I want to just simply use a value of 3,000 meters, knowing that this will give us something of a decent result. So 3,000 meters for the maximum radius of the neighbourhood. And finally, we have a field name for within our new grid or mesh, and we're going to call it interpolated log of iron. And the next step is just to finish and watch the working of the interpolation underway. When that's completed, you can see we have a new mesh available to us. First one is the point mesh above, but the new one is here, log of iron, with our new field. One thing to do now, before we go on, is to remove the linearization. So, in other words, we want to revert it back to a log normal distribution. So using our new field in the new mesh, we need to right-click, and we need to again create a new field on the mesh. And so the idea now is to ask for the exponential of the interpolated log of iron and close the bracket. And the name of this new field is simply going to be called interp of iron. Evaluate. And save and exit. And now we see a second field pop into the new mesh. Let's visualize that new mesh. First of all, I want to hide the current point mesh so that we can visualize what we've just created, which is the inverse distance interpolation of the log of iron, which has then been reverted back to a log normal. Now in the 3D viewer, you'll see the result of what we've done. And that is the result in 3D. Of course, you can use the clipping tool as before we've seen. So that's on the bottom of the toolbar on the right hand side. Taking across and sliding through at any point from the bottom or from the side. You can scroll through this mesh in a number of ways. Next, what we'd like to do is think again and return to our geological model. So just to remind ourselves what that looks like, and we'll hide the mesh for a moment. Our 3D geology model, once computed, at a reasonable resolution will allow us to return to the thought that we have some geological shapes, and we may be able to now proceed towards masking in terms of those geological shapes. The green one is the ore2 body, and that's what we're interested in masking with. And that is why our next step will be about producing a current model field within our mesh. So a little plus here has come up, and that's because we now have our smooth geology model available to us. Remembering we can hide everything except perhaps return our ore2 geology body. So let's show that now. This is the one of interest. This is something we're going to mask with now. So in order to do that, we can just show, or rather hide, the smooth geology for the moment. And we're going to think about adding those values of the current to the current mesh. Let's right click now and say add a current model field. This step will take a few moments. It's harvesting the geology into the current mesh, and we can view it now. When you first do view one of these meshes, you can see that there's grey here for the airspace above the topo. That's entirely expected. If you do a right click and choose to say edit colors and clips, you can actually clip that to not be seen. So change that value in the visibility clip to 0.5 through to 5 and apply that. And now we can see we've taken away the above topo material and our model is left below. But whereas before it was a smooth geology model, this is now a discretized geology model because it represents the same extents and resolutions of our log of iron mesh. Also, it's interesting to note that the color table has picked up the lithology, and that's what we hoped for. It matches the same as that in the GeoModeller model. Now just closing that, we can be sure that what we're working with now is this value. One thing I just also needed to show was that it's important that we distinguish the ore2 geology body for its identity number, and in this case it's identity number 4. So we can now use that knowledge. So now we're going to create a new mesh which is going to contain the interpolated iron grade masked by the ore2 mesh. And so from our main mesh we're going to select to compute a new field, and this time we're going to say if the current model grid is equal to 4, which is our known ID for ore2, then is a delimiter, give us interp of iron, otherwise give us a null, and close the brackets. So with this statement we would like to designate the name of this new field to be called interp of iron by ore2. Now the idea is to evaluate the new field and save and exit. So now we have our newest mesh available to us in the field below here, and we can show it in the visualization in 3D. And what's been presented here is nulls in every position which doesn't contain ore2 geology. Another thing you may want to do is clip the iron grade to, say, some level greater than 55% and then retrieve the volume. So now let's try that. From our main mesh, we can hide all the views of this mesh, but the idea again is to compute a new field, and this time the argument will be if interpolated iron is greater than 55, then give us interpolated iron, otherwise give us a null and close the bracket. And this field name, we can call it interp of iron greater than 55. And evaluate and then save and exit. When the new field is created, we can visualize it in the 3D. And now discover what has been produced is a different mesh, this time only sticking with all grades greater than 55%, and everything else becomes a null. Just another way in which to manipulate meshes by the 3D calculator. We are also able to have a look at the volume of this by a simple method. Just firstly checking that indeed the histogram shows a cutoff point at 55% iron as expected. And we can apply a different colour stretch there if we wish as well. After the volume now, let's go to histogram. What we can see now, again, is this cut-off histogram at 55% iron, and what's a very simple and quick way to work out the volume of iron, which is in the model at greater than 50%, 55%, is to say that the number of effective cells here is 66,618. So this is very much less than the total available cells at 278,880. So as a fraction of the total model, we can see that these are the number of cells that are filled. And if we were wanting to know the volume of ore at greater than 55%, it would be simply a matter of reminding ourselves the cell dimensions here. 25 meters by 25 meters was what we set for this resolution of the mesh, and it's a simple computation to multiply the number by a square cube of 25 meters by 25 meters. I think I'd like to finish up today, mindful of keeping within the hour. The interpolation method we've shown here today is only the very simplest, being a linear interpolation method, and it will not be able to provide nearly as good a result as what other interpolation methods are available, such as domain kriging and 3D methods of kriging. This is just one little run through the wizard of one of the interpolation methods, the most simplest and probably the least accurate in this situation. So to finish up today, I want to return to our PowerPoint. Remind us that the webinar is going to be up on YouTube, and you can see this April webinar along with all the others which have been recorded since January on variable topics. Also, I'd like to invite you to join our Q&A Google group with the address below, and we would welcome you to post a question there. We are very keen to continue discussion, particularly on this month because we haven't had the advantage of a live webinar. And finally, if you wish to take a 4 free-week evaluation license for GeoModeller software, please contact us. either directly via our website, or you can contact me. My name is Helen Gibson. I'm a geologist and I'm the Technical Sales Manager for Intrepid Geophysics. So please email me on helen@intrepid-geophysics.com. I look forward to hearing from you. Thank you.